Okay, so here we are on page 5 of our differential equations packet, where we're going to be writing and solving differential equations analytically. The last section we solved them graphically using slope fields to find the general solution, and then trying to draw one particular solution through an initial condition, through a point that we had to draw that solution through. Now we're going to take an equation, we're going to solve it analytically to find the general solution, then take a particular individual point, an initial condition, to find the particular solution. So let's start. It says here, if a differential equation is equal to itself times an arbitrary constant, that is to say, if dy dx is equal to k times y, then the function must be. Now, if we think back to our rules for derivatives, we dealt with a function where when you took its derivative, you got the same thing as the original function times something. Sometimes it was a constant, other times it was just another function. And in that case, that was the exponential function. So when you have a differential equation whose derivative is equal to k times the function, then the function is going to be exponential. Usually it's going to be of the form y is equal to e to the x, or something of that nature. Okay, so we'll have some constants here as either coefficients of the function e or the function x. Next, we're going to see that we have this phrase directly proportional and inversely proportional. Now, if we go back to similar figures in geometry, when we said that two polygons that were similar had congruent angles, corresponding angles were congruent, but we said corresponding sides were proportional. So if one of the sides of the second figure, the similar figure, was longer than the corresponding side in the first, well, then they were all going to be longer. So in other words, the phrase directly proportional means that as one increases, so does the other. So in other words, as y goes up, then x is going to go up. Or as y goes down, then x goes down. And so the function type that does this is going to look something like this, where if you have y is equal to just something times x. And again, go back to the geometry to similar figures. If one of the sides was 3 times the other side, then every side in that similar polygon was going to be 3 times the original polygon. Inversely proportional would be just the opposite. That is, as y increases, then x is going to decrease. And a function of this form is going to look like y is equal to k over x. So those are the 3 types of functions that we're going to be working with more than anything else. Okay? Let's take a look at example 18. A population of insects P in a region will grow over time T at a rate which is directly proportional to their current population. Write a differential equation that describes this relationship. So what we're told is the population will grow. It's going to change at a rate directly proportional to their current population. So that means the population is going to change over time at a rate that is directly proportional to their current population P. Okay, and we only have to write the differential equation. We're not asked to solve it here. Example 19. The population of rabbits R in the woods behind the school grows at a rate, here it is again, proportional, and it's understood when they say just proportional that it is direct, so directly proportional to the product of the number of rabbits and the difference between the size of the population and the maximum population M. Write a differential equation that describes this relationship. So again, the population of rabbits grows at a rate, so we're looking at dr dt is equal to, at a rate proportional to the product. So it starts off with our constant of proportionality, our k, times the product of the number of rabbits, which is r, and the difference between the current population and the maximum population m. Now, the word difference in math, for the most part, is a positive answer. So when we do the difference here, I want the larger number over here minus the smaller number. We could get around that by using an absolute value, and then the order wouldn't matter. So in this case here, the population of rabbits will always be less than the maximum population M. So we're going to go ahead and put M minus R. Example 20. The rate of change of the volume of helium in a balloon with respect to time t. And again, that whole phrase right here, from there to there just says dv dt is inversely proportional to the cube of the volume. So inversely proportional means it's going to be k over the cube of the volume. Now, when we're dealing with exponential equations, or when we're dealing with population growth, I should say, populations tend to grow exponentially. And they're going to have the differential equation that we talked about on the previous page of dy dx is equal to k times y. Now, the differential equation produces the function y is equal to c e to the kt. Now, just real quick here, we've worked with exponential functions in the past. Last year we saw this one, a is equal to p e to the rt, where again p is what the initial principal is when you're working with compound interest, r is the rate of growth, t being the time. We then moved into half-life, and we saw we could use the same formula. The quantity is equal to the initial quantity, e to the kt, where again k was the rate of growth. Because we're dealing with exponential decay, k was negative. We're back here where compound interest, r is positive because the rate of growth of money is generally positive. So what we're going to do here is we're just going to use the same essential function. We just use a few different little variables. So c, representing just a constant, actually stands for, right here, the population at time 0. Okay. The reason being is if time is 0, 0 times any k would be 0. E to the 0 power would be 1 times c is c. So c is the initial population, but this c e to the kt is going to be our general form for exponential growth, usually or quite often dealing with population. And let's just see for a second, if I derive both sides with respect to time, I get dy dt is equal to c e to the kt times the derivative of kt, which would be k. Now this c is a constant, this k is a constant, so dy dt in this case would just give us some new constant, e to the kt. So notice we're getting the same function back. So dy dt or dy dx, if we were dealing with x, is going to be just some c e to the kt. Okay. In the next video, we're going to go ahead and we'll take a look at example number 21. We'll look at what happens with some population questions here.